Well, whatever.
Abelianization. Yeah, it's a tricky word. Thank you very much for inviting me. So yeah, that's indeed the title of, let's see, and it works. Yeah, so this talk will be sort of centered around a couple of themes. So starting probably with topological string theory on the very top. So I guess all of you know a little bit here about topological string theory. So it's some simplified version of string theory with the target space a Calabi-Yau manifold. So there are various invariants and partition functions that one can associate that come out of this topological string theory. It's also very closely related to integrable systems. There is an integrable structure, in particular, the Hitchin integrable system will play an important role in this talk. Then it turns out that we can get more information about this, or we can find some nice geometric structures by looking at various differential and difference equations associated to these theories. And we'll also see that certain spectral networks play an important role. So this talk is based on two papers, one with Philip Ritter and Richard Sabo, and one with one recent one with Murat Alim and Ivan Tuli. Right, so what I want to start out with is sort of so what I should have said. So in this talk, I will consider everything from the perspective of supersymmetric gauge theory. So there is a duality between topological string theory and supersymmetric gauge theories. And so my perspective will in this talk will be from the gauge theory side. So I want to start out with saying a little bit about a partition function that comes up in the gauge theory context, which is the famous instanton partition function for, in this case, so I will start by considering 4-dimensional gauge theories. Later on in this talk, I will go to 5-dimensional ones, which are immediately related to topological string theory on Calabi-Yaus. Well, this instanton partition function, you might know this function. So it's a sum, formally a sum over some instanton parameter to the power k, the instanton number, times an integral over a certain moduli space of instantons in this gauge theory. If there is also matter in the theory, then this integral will become an integral over some Euler class, which is associated to the Euler class is of a bundle of solutions to the Dirac equations corresponding to these to this matter. Right. So this instanton partition function, it's well defined mathematically if you turn on what is called an omega background. That is, if you compute these integrals equivariantly versus the green, this green.
Just read out what's written.
Okay. Well, there will be some other green as well, I'm afraid. But maybe is it just a light green, the very light green, or is it also this?
Just a bit dark.
This is okay, but this is, well, there's 2 light greens. This one and this one is even lighter. Maybe. Okay, right. Yeah, so what is well, I mean, this is the more general formula anyway. So on this slide we don't have any issue. It's instanton parameter. So that refers to this Q here. And here it says moduli space of instantons. Sorry about that. Right, so this instanton partition function, and maybe we should consider this one, the more general one, which everyone can read. It has a number of contributions. So it has a classical part, it has a so-called one loop part, and an instanton part. So the classical part has this really simple form. It's just an exponential where tau is the complexified gauge coupling and A is a Coulomb parameter of the gauge theory. The one loop part can be expressed in terms of certain special functions. In particular, it's the Barnes double gamma function, which is important. And then there is the actual instanton partition function, which can be written at least as a sum over Young diagrams, where all the fields in your gauge theory have a certain contribution. So the vector contribution, the vector multiplets contribute with this vector, and the matter ones with that vector. Right. So this is the structure. I just want to tell you what the structure of this instanton partition function is. Right. So I'm going to spell this out. So the log of this Nekrasov Z-Nek, it says the Nekrasov partition function, in an expansion in these equivariant parameters, epsilon1 and epsilon2, it starts off with this divergent piece, which is 1 over epsilon1, epsilon2 times some gadget, which is called F0. This is the holomorphic prepotential. And then it has some terms regular in epsilon1 and epsilon2. By the work of Seiberg and Witten, we know that this holomorphic prepotential has a geometric interpretation. So there is a so-called Seiberg-Witten curve associated to any n equals 2 theory. And right, so we can take a basis of A cycles and B cycles on that Seiberg-Witten curve. And then the periods, which are defined with respect to lambda, this is the Seiberg-Witten one form, it's the Seiberg-Witten differential, or well, we'll see it in some more detail later. But once we define the periods A and A dual, we can extract this holomorphic prepotential from this equation. So it's a relation between these A and B periods. So notice that this is a completely algebraic description, well, at least of the partition function. So in this talk, I will show you that there is also another perspective, so a more analytic perspective on these algebraic objects. Right, and so there will be two main examples in this talk. Right, so we're going to consider two examples of four-dimensional n equals 2 theories. Well, if you want to be precise, these are theories of class S. That's where, so for all theories of this class S, this what I'm going to tell you is going to work. And what does that mean? It means that the Seiberg-Witten curve that we just saw, that this is the spectral curve of some Hitchin integrable system. So that's basically the definition of these theories of class S. They are dual to Hitchin integrable systems. Well, there's one very simple example, which is sometimes called the Ad2 theory. This is a theory where you don't have any gauge fields, but you just have a hypermultiplet in physics language. Its spectral curve, the Seiberg-Witten curve, is non-compact, and it has this form. It can be written at least in the form W squared is equal to C squared plus M, and this M is the mass of the hypermultiplet. Well, this so it's a spectral curve. It's a double covering, a branch double covering with two ramification points over just a complex plane, and the Seiberg-Witten differential in this case is just equal in these coordinates equal to W dz. There is a more sort of complicated example, which is the pure SU2 theory. So in that case, we don't have any matter, but we just have an SU2 gauge group. The corresponding cyberequivalent curve for this theory, it can be written in this form. Again, it's a quadratic equation in W. Lambda here is the scale of the theory. And U is what is called the Coulomb parameter. So again, this cyberequivalent curve is a double covering, a ramified double covering, in this case over, well, you could say over P1 minus the points at 0 and infinity. So the ramification points at these punctures as well as at two other points. So in this talk, I will also be interested in a sort of special limit of these Nekrasov partition functions. So as we saw before, in general, they depend on two equivariant parameters. So what I'm interested in this talk is, in particular, this limit, this Nekrasov-Shatashvili limit, where you take one of these parameters to go to 0. So this limit, it corresponds to looking at the four-dimensional theory on the product of these two planes, where you only have an equivariant parameter in one of the planes. So that means that effectively, your theory becomes a two-dimensional theory on this plane, and it becomes an effective n is equal to 2,2 theory on that plane, which has an effective twisted superpotential, as it's called. And that object I'm denoting, well, here with W tilde, but in general with W. And it can be written, well, as found by Nekrasov and Shatashvili, it can be obtained as a limit of the complete Nekrasov partition function. And again, it starts out with 1 over epsilon times this prepotential. So this superpotential, it's also sometimes written as FNS. Maybe that's more from, especially in the topological string literature. I think that's the notation that is used for it. So I think, yeah, in the rest of the talk, I will denote it by W 4 dimensions because it comes from a four-dimensional gauge theory, and NS because yeah, so we obtain it in this NS limit. Where this in the first example, this 82 example, where we just had a hypermultiplet, the superpotential is very simple. It only has a one-loop contribution corresponding to this hypermultiplet, and so it can be written in terms of a special function, which is the y function, which is just an integral of a ratio of gamma functions. In the pure SU2 theory, things become more complicated. So in that case, we've got a classical contribution to the gauge field. We've got the one-loop contributions, and we've got this instanton series. What will also be important is that this Nekrasov-Shatashvili limit, this effective theory on R2, it has a geometric description as quantizing this Hitchin integral system, which we met. And the quantization parameter is this complex parameter epsilon. So, for instance, if you consider this pure SU2 theory, then the quantum Hamiltonians for this quantized Hitchin system, they are obtained by quantizing the cyberequivalent curve. So they're, in this case, they're the quantum Hamiltonians are parameterized by this family of what are called SL2 opers, which can be written in this particular way. So they're differential operators of degree 2. So to describe this this quantum Hitchin integrable system in full, you'll need to consider what is called a spectral problem. So you need to consider letting these quantum Hamiltonians act on some wave function psi, where psi takes value in some particular class of functions. So I won't spell out all the details of these spectral problems in detail, but rather what I want to do is, so I want to start by just saying that this wave function, suppose that we approximate it in the WKB way. So suppose we just write it as e to the power 1 over epsilon times the integral of some function s, which also depends on epsilon, and which we can write as a formal power series. So suppose we do that, we consider this problem sort of in this formal way, then we can associate to this problem quantum periods, which in this case are also formal power series in terms of epsilon, which are just given by the periods of this function s over A and the B cycles. And it turns out that, well, so it's a bit silly that this is not readable. If, yeah, maybe that's right. So the relation that described the prepotential gets generalized. And it turns out, so this is the dual periods, AD, the dual quantum periods. These are the dual A periods. Sorry, these are the quantum A periods. And so this Nekrasov-Shatashvili superpotential is given in the same way as before, but now in terms of the quantum periods instead of the classical periods.
What's top of the
This is 4D.
4-dimensional.
Yeah, 4-dimensional. So this is the 4-dimensional one, right? And so in the epsilon going to 0 limit, this reduces to the classical relation that we sort of started out with. So this is a way to recover this superpotential, at least in a formal epsilon expansion from this quantum geometry. So I can't read this, so let's see. Right. So the question is, can we obtain the exact result as well? So can we obtain the superpotential as an exact expression in epsilon? And to see how that would work, consider this Ad2 theory again as our example. So we've seen what the spectral geometry is. In this case, right, the corresponding oper is again a second order differential equation. It's basically a naive quantization of our spectral curve. And you might also recognize this as just a Schrödinger equation for a complex harmonic oscillator. Now, the Schrödinger equation, it has, since it's of order 2, it of course has 2 independent solutions. But for later purposes, I'll introduce these psi1 up to psi4 And I'm not going to write them on the board. Maybe it's not that important. So psi1 of C is equal to, right, this is actually maybe a bad notation. So this D of mu is now not a differential operator, but it stands for an integral representation of a Weber parabolic cylinder function, which is, I mean, which you should be able to read. All the others, so what I've written here is psi1, which is equal to d mu as I spelled here, this cylinder function with argument square root of 2 over epsilon times c. Size 3 is defined as that with some phase in front of it, which is dependent on mu, and a minus in the argument. And then I've got psi2 and psi4 here, which both have some phase, which is dependent on mu. And in their argument, they have an additional factor of I. So these are four linearly dependent solutions to this Schrödinger equation for the AD2 Oper. So the claim that I want to make is that the superpotential, if you want to get an exact expression for it in epsilon, then you might compute it as well by this integral over the log of a square root of Wronskians. So this is the Wronskian of psi1 and psi4, etc. So as the square root of a ratio of Wronskians of these four solutions, of these four parabolic cylinder functions. And so you get the same result as we saw that we should be getting, namely this particular y function, which contributes to the one loop factor of this superpotential. Right, so what I will do in the next few slides, I will try to explain why this is the case. So why we can write this superpotential in this way. And so the idea behind this is that that W can be obtained as a Borel sum of its formal epsilon expansion in the direction where the argument of epsilon is equal to pi over 2. So let's see how that works. So if we've got this Oper, then this differential equation, then we can write down a basis of formal solutions. And you can't read this, but it's the same except for there's a minus sign in the first factor, so it has different asymptotics. And yeah, the other factors are slightly different as well, but that's not really important. Where this t is related to our coordinate z by this rescaling. So in particular, we've got one solution which is decreasing fastest along the reals, and we've got the other solution which decreases fastest along the imaginary numbers. Right. So, what is the definition of a Borel sum? Borel summation. So, if we have a function, a formal power series in T, say, then we can construct the Borel transform of that function. And if we integrate that Borel transform along a array which has a certain phase, theta, then that gives, then that object has better convergence properties in general than the formal power series that we started out with. And this is, well, I think I have another notation for it later, but anyway, so this I would denote by the Borel sum of this function f of t in the direction theta. So this is going to be important. Right. So suppose now that we fix some of these parameters in this theory. So suppose suppose that the mass of this hypermultiplet is greater than 0, and suppose that we fix the argument of epsilon to be equal to pi over 2. In that case, we get that these two formal solutions, that one of them, so the psi minus solution, as it says here, the formal psi minus solution, it decreases fastest along this diagonal, and psi plus decreases fastest along this diagonal. Now, these solutions that we introduced before, the psi 1, the psi 2, the psi 3, and the psi 4, they can be obtained as Borel sums of psi minus and psi plus along a certain ray in the z plane or in the t plane equivalently. And these Borel sums, they can be analytically continued in such a way that the solution psi 1 is defined in this half plane, whereas psi 2 is defined in this half plane, psi 3 is defined in this half plane, and psi 4 is defined in this half plane. So in each of these quarters, in this configuration, we have a basis. We have a basis of two solutions to the Schrödinger equation, which are well behaved. Right. So why did we set this argument of epsilon to be equal to pi over 2? Well, this is a very special phase for this geometry, for this n equals 2 theory, because the hypermultiplet, it has a central charge, and the argument of the central charge is exactly equal to pi over 2. So the way to visualize this is in terms of what are called spectral networks. So suppose I'm drawing the trajectories of this particular function. So where e to the power minus I theta times the square root of z squared plus m. So that was the part of this spectral curve, the differential that defines the spectral curve. So suppose that I restrict. So suppose that I want to look at trajectories for which this is real. Then if I draw that for theta smaller than pi over 2, I'll get a picture like this. So at each of these two branch points, these ramification points of the spectral covering, I get 3 trajectories that are being emitted, and they all end up at infinity. If I tune my phase to be special, to be equal to pi over 2, then 2 of these trajectories, they start to overlap, and I get what is called a saddle trajectory, which is connecting these 2 branch points. And if I make the phase larger again, I get sort of the opposite picture. So this phase is where something special happens. And according to the work of Kyoto Moore-Neitzke, this saddle trajectory exactly corresponds to the hypermultiplet that is defining this theory. Right, so suppose now that we consider this over the Schrödinger equation, the epsilon. So that's what it says here. Consider over the epsilon as a flat SL2C connection, nambla epsilon. So suppose we do that. Every differential equation on a Riemann surface, we can also consider that as a flat connection. In that case, we can bring this flat connection in a very special in a special gauge. We can bring this in a gauge such that the flat connection is abelianized in either of these regions outside of the spectral network. And so it's abelianized in each of these regions, but if we cross one of these trajectories, there will be a non-diagonal gauge transformation that connects them. So in this case, it turns out that these psi's that we introduced, that we found through this Borel transform, that these provide the basis of this abelianization. So, right, so that's what it says here. So in particular, in this region, we've got a basis given by psi 3, psi 2. So that's a basis that abelianizes this flat connection, at least with respect to the spectral network that is drawn here. On the other hand, if we cross one of these trajectories, then we have this off-diagonal gauge transformation, and you can write it in two ways. You can write it as psi 4 is related to psi 2 by some off-diagonal factor, or you can write it in terms of the Wronskians of all of these solutions. Right, so now let me introduce the A cycle and the B cycle in this case. So as the A cycle, I take the one cycle that goes around these two branch points. The B cycle is a bit more subtle, so that's a non-compact cycle in this geometry. So what I'm secretly doing is I'm fixing the gauge at infinity. So this is a well-defined period. And then I can express what are called the quantum periods, but what are now the exact quantum periods in epsilon. I can express them in terms of the Wronskians of all of these functions. In terms of the basis that we've seen before. And that gives us an exact relation between the exact quantum periods, which reproduces this this W as an exact function in epsilon. So that was a very simple example, just to show you how things work. But you can do this for more complicated theories as well, such as for this pure Ad2 theory. So in the pure Ad2 theory, the spectral geometry was given by this elliptic curve, this torus, which was ramified over the complex sphere. And in that case, the corresponding opers or quantum Hamiltonians are parameterized by this family of differential equations, which you might recognize as the Mathieu differential equation. Let's see. So suppose we consider the recoupling regime, where the scale is much smaller than the Coulomb parameter. So in that case, we can introduce another sort of convenient basis of solutions to this Mathieu equation. And so we've got three regions in this case. The region near c is equal to infinity, the region near c is equal to 0, and this tubular region. So suppose I give them the names psi1 prime, psi2 prime, psi1 double prime, psi2 double prime, and psi1 and psi2. Then I can define these. Then I want to define these solutions in a certain way. So psi1, for instance, I want to define as the asymptotically small solution to this Mathieu equation when I approach this puncture along the negative real axis. And similarly, psi1 prime, I define as an asymptotically small solution near this puncture if you approach this puncture in a particular way. And psi 2 double prime here is the this asymptotically small eigenvector of the monodromy around this tube. So they're all defined in that way when theta is restricted in a certain way. So it's again, the argument of epsilon is again taken to be pi over 2, and we're in this weakly coupled region. With these definitions, one can express this superpotential again as in terms of a ratio of Wronskians of these solutions. And it now looks like this. So you can verify this in perturbation in this lambda. That's how you usually compute this epsilon partition function. So it's exactly an epsilon, but in a perturbation in lambda. And you retrieve the very familiar form of this superpotential. Right. So what is the idea of that computation? So basically, we have to compute the monodromies of this Mathieu differential equation, not only along this A cycle, but also along a cycle which stretches in between z is equal to 0 and z is equal to infinity. So what we may do is we may introduce a new coordinate near this z is equal to 0 and compute these psi 1 and psi 2 in that region in a series in lambda squared. We can analytically continue these to phi is equal to infinity while keeping z approximately equal to 1, and then reorganize it as a series in lambda squared, and then compare them to the eigenfunctions of the monodromy around this neck. So that gives us a way to compute this ratio of Wronskians. There is also a physics interpretation of that computation, which is spelled out in the paper by Nekrasov and you. That's in terms of surface defects, the surface defects that wrap this omega deformed plane and are just a point in R2. So their moduli space is the whole surface. So you can insert them at any point. And these psi's, they have the interpretation as surface defect VEFs. So they are vacuum excitation values of these surface defects. So why in this case do we consider, well, why did we take this phase theta is equal to pi over 2 to get this superpotential? Again, this is a special phase for this theory because the W bosons in this, the W bosons in the gauge theory that provide the low energy description of this theory, they have a central charge which again has argument pi over 2, and the corresponding network that you can draw is of this shape. It's again made up out of these saddle trajectories. So all of these lines here, this one that connects the branch point to itself as well as this one, they're all saddle trajectories. And the solutions that we defined, again, they are the local basis for an abelianization of this operator, of this Mathieu operator d epsilon. So in this case, the trajectories are given by this constraint, which again comes from the Sauer-Witten description. Right, so this is what I've already said. So we introduced 2 cycles on this elliptic curve, and using this description, we can write these exact quantum periods in terms of these functions, in terms of these this basis of functions, and then this is the relation that allows us to retrieve this superpotential. So this might be sort of rephrased a bit more mathematically. So what we've really been doing is we've been computing the generating function of opers in terms of a special set of Fenchel-Nielsen coordinates, a special set of Darboux coordinates on the moduli space, underlying moduli space of flat connections. These exact WKB, the exact quantum periods, they correspond to a set of spectral coordinates which are found by this abelianization. And so the opers, they are given by these differential equations that correspond to the quantum Hamiltonians of the corresponding Hitchin system. So now you might wonder what happens if we don't impose this constraint, that we set this phase theta, that we fix it. But suppose that we compute the Borel sum in some other direction, and then analytically continue in epsilon to get a holomorphic function in epsilon, or a meromorphic function. Right, so we can do that equally fine. So that's what this formula says. So here the A exact are the exact quantum periods, but now with respect to any theta. So again, we can define these periods. We can define them as spectral coordinates, or we can define them by Borel resumming. And so this then gives us a new object which will differ from the gauge theoretic expression, and so it will jump by some factor. So this will define what we've called a generalized superpotential. And so this has a quite nice interpretation in terms of in 5 dimensions. Let's see, I'll say a bit more about that. Right, so this object, this generating function which depends on theta, on this general theta, it's an object that is piecewise constant in theta, because it only changes when the spectral network changes. And for instance, for the pure Ad2 theory, you can make this diagram where each of these factors correspond to a phase where the spectral network, a phase of theta, where the spectral network jumps. So it will jump here. Well, it will jump at theta is equal to 0, and it will jump. So there's an near this phase pi over 2. There is like this dense set of phases that collapses to that particular phase. So in each of these regions, in between these what are called active rays, in each of these regions, we can associate to that a superpotential, a generalized superpotential. And if we cross a ray, if we cross such a ray, then the superpotential it will jump with a factor which is proportional to a dilogarithm in terms of this exact A period. So yeah, let me skip this one. So this general object is quite interesting because it then encodes. So these jumps, these active rays, they correspond to BPS states in 4-dimensional theory by the theory of Goyotto, Moore, and Neitzke. So that means that this generalized object, it sort of encodes all these BPS states. Geometrically, you might also see it as a section of some distinguished line bundle. on the underlying moduli space, and that's this line bundle has played an important role as well in these works that I've written down here on the right. We'll come back to that in the last part of the talk. What I want to add here is that in the four-dimensional gates theory, this theta, it actually has an interpretation as well. So whereas, right, so what is the interpretation? So it corresponds to some IR boundary condition that you put on this half omega background at infinity. So it's, right, so it's, yeah, so, well, to phrase this, let's see, so not sure whether I want to spell this out in detail, but we may equivalently change the metric of this half omega background a little bit, and then it becomes a cigar with a circle at infinity. And we can couple a three-dimensional n equals 2 theory to this circle at infinity times R2. And so if you do that, you get a different boundary condition for your original four-dimensional theory. And the superpotential corresponding to that theory, so the coupled system of this n equals 2 theory that we started out with, together coupled to this n equals 2 theory, that gives you this new superpotential, which is labeled by theta. Right, so in 5 dimensions, it turns out that there is a quite similar story. So first of all, let me say that these four-dimensional gauge theories of class S, they may be lifted to 5-dimensional theories. And these 5-dimensional theories, they are by geometric engineering, they're related to topological strings and to mirror symmetry. So I guess I hope you're very familiar with this. So at least the most standard examples of this mirror symmetry, they start out with toric Calabi-Yau threefold, which then by mirror symmetry gets related to local Calabi-Yau, which is what is called modeled on a certain curve, the mirror curve. And what is special about this curve is that it's embedded in C star times C star, and that the corresponding Seiberg-Witten differential is expressed in terms of the logarithm of these coordinates x and y. So by geometric engineering, this is related to a 5-dimensional theory on R4 times S1 with some radius beta. And if we send that radius to 0, then we get a 4-dimensional theory. So the 4-dimensional theory is related to a 4-dimensional Seiberg-Witten curve. This lifts to a 5-dimensional Seiberg-Witten curve for this 5-dimensional theory. And that 5-dimensional Seiberg-Witten curve is exactly the mirror curve in this picture. So that's the gauge theoretic interpretation of these mirror curves. So the topological string partition functions, they are related to 5-dimensional instanton partition functions. These are the k-theoretic instanton functions, which are defined well by some index. And again, we can take this NS limit, where we set one of the equivariant parameters to 0, and we get that defines this object W 5 dimensions, the 5-dimensional superpotential, which starts out again with a 5-dimensional version of this prepotential. In terms of integrable systems, these objects are related not to the usual Hitchin integrable system, but to a multiplicative Hitchin system, for which the spectral curve is embedded in C star times C star with this particular differential. So, so what I've told you before can be lifted to 5 dimensions. So many of these ingredients are available to lift this whole story to 5 dimensions to the setting of topological string theory. In particular, this multiplicative Hitchin system has been studied by many people. It's related to the modular space of periodic monopoles, and the corresponding differential equation. The differential equations are replaced by difference equations in this case, which are also known as Q-opers. The whole story of spectral networks has been generalized to 5 dimensions. They're called exponential spectral networks or BPS networks, exponential BPS networks. Well, this physics interpretation of these wave functions in terms of physical objects, that's also available. These are now the surface defects in this particular background, and they correspond to B-branes ending on the mirror curve. So probably the simplest example here is that of the resolved conifold, which is in terms of the toric geometry is given by this bundle over P1, and by mirror symmetry it's related to this particular mirror curve. And here I've switched from small x and y's to capital X's and y's. So these are the C star coordinates, x and y. Q is related to is e to the power 2 pi I t. Well, it's not written here, but maybe later. So this is a curve which is embedded in C star times C star, and it has a double covering. Well, you could view it as being double covered over one of these C star planes. If you do that, then in the 4D limit, if you take the 4D limit, this is related to the Ad2 theory, this other simple example that we've seen in this talk. So in particular, this spectral curve will reduce to the Ad2 Seibertson curve. So that's how all of these things are connected. Right, so this corresponds to a 5-dimensional abelian gauge theory. This abelian gauge theory has again a spectrum of BPS particles, of 5-dimensional BPS particles now. And these BPS particles, they can be divided into 3 sort of powers, towers of particles. So there is a tower corresponding to 1 D2 brane plus k d0s. There is the tower corresponding to k d0s, and there is a tower corresponding to minus d2 plus k d0s. So all of these BPS states, they can be visualized in terms of exponential spectral networks for this geometry. Again, we have a similar picture. So these spectral networks, they jump at certain phases, and these phases are illustrated here. So each arrow corresponds to an active ray, and in particular, this phase corresponds. I've denoted that by theta np. It will stand for non-perturbative later, which is just the argument of the central charge for the D2 brane. And then this phase corresponds to the argument of the central charge of the D0. So these are all the phases where this network jumps, and where all these BPS states can be visualized. So in the 4D limit, what is called, well, maybe you remember that I had this beta, which was the radius of this 5-dimensional circle. So in the 4D limit, that the beta goes to 0, and this whole tower, well, these 3 towers of BPS states, they just reduce to the 4D BPS hyper and its antiparticle of the Ad2 theory. Right, so let's see how much time do I have. I'm out of time, right? 5 more minutes, okay. Okay, that should work. So the effective twisted superpotential of the 5-dimensional abelian theory, we may compute them, it turns out, in 2 ways. So we can either compute the Borel sum of okay, right. Let me start by saying that so from the gauge theory, this superpotential again has only a 1-loop contribution. In this case, it can be spelled out by this infinite sum. So the effective superpotential, it turns out, it can be found by Borel resumming this. And it could also be computed by Borel resumming the quantum periods for this geometry. Let's see, I think I'm going to explain this in some more detail. So first of all, so how should we think of this Borel sum of this particular function? So this is very similar to the previous work of Alim, Saad, Twilly, and Teschner in the context of the usual standard topological string. So again, we can Borel sum this expression in each of these directions. And what we find is that there are 2 distinct phases. Namely, there is the distinct phase corresponding to this accumulation ray, where all these rays come together. And that Borel sum gives us back the original answer, the Kopekuma-Vafa answer. Whereas if we do it if we Borel with in some other direction, then we'll jump every time that we cross these rays. And we jump by a factor which is again dilogarithm. And then there is sort of the other interesting way where we find that this Borel sum can be written as the original Kopekuma-Vafa expression, but then plus an extra piece, which is basically the S-dual of the original expression. And it has this particular formula. So this is a bit similar to some older work of Marcos Marinho and collaborators in the context of the standard topological string, where they also found that there is a non-perturbative description of topological string theory, where you do not just have this Kopekuma-Vafa expression, but where there is an additional piece. So what is special in this NS limit is that in this NS limit, this non-perturbative superpotential is actually exactly, well, it's self-dual under this change of parameters epsilon, and also t should be mapped to 2 pi t over epsilon. So it's precisely self-dual under this S duality. Right, so don't have much time, so let me skip through. So there is the second picture where you consider this Borel sum from the perspective of quantum periods. So in that case, you consider a difference equation associated to this conifold, as well as its wave function. You can write this wave function again in the WKB approximation, and you can then Borel resum it to find the exact A and B periods, which now depend on the direction that you've Borel resummed it. And so what you find is that this B period in particular, it can be written as the wave function evaluated at this puncture divided by the wave function divided at this puncture. And if you normalize that B period, then indeed you find that this is related to the superpotential in the way that we would expect it. Right. So so the last thing that I want to mention is that this Nekrasov-Shatashvili perspective, in terms of a generating function of opers, it can be generalized as well. So these exact quantum periods, you can again interpret them as spectral coordinates on the corresponding moduli space. There are two sort of very degenerate networks that play an important role there. In particular, so there are two special phases, as we saw. One phase where we recover this Goba-Klava expression. So that's the gauge theory expression, which corresponds to W being a generating function of Q difference opers in terms of one type of special coordinate. And we've got the other phase where we find this S-dual expression, which has these nice non-perturbative properties. Right. So so that's basically what the end of this talk. So what I want to conclude is that in both 4 dimensions and 5 dimensions, this instant partition function that we started out with, it can be reformulated analytically using abelianization techniques or equivalently exact WKB techniques as a generating function of epsilon opers or Q opers in terms of a special kind of Darboux coordinates. And as an example, maybe the most interesting example that we've seen is this superpotential for the 4-dimensional Ad2 theory. But so equivalently, you can compute this the superpotential as the Borel sum of its epsilon expansion in a certain critical direction, which I've denoted in this way because that's the final expression that it gives. But other phases are very interesting as well. So all the jumps, they can be interpreted in terms of boundary conditions of your 4 or 5-dimensional gauge theory. And then there is a special sort of opposite phase, theta non-perturbative, where you find these this partition function with these interesting S-dual properties. So so that's it. Sorry, what was the last? Do you have any idea why it works? Whether it works for? Oh, okay. Yeah, so that's a really good question. So that's what we're looking at the minute. Yeah, so we're optimistic, but yeah, this is yeah, I don't know yet. So it has I should say there's a family of Hamiltonians. There are some parameters right in the. But it Well, yeah, right. That's right. That's right. I mean, that's. Well, you can consider any spectral curve of any genus. It's indeed true that there is one difference equation. So the mirror curve can in principle be of any genus. So you're right that there is one Hamiltonian, but it has a lot of moduli. So in terms of the quantum periods, you can think of it again. Well, so so maybe I should say, so to get this gauge theory perspective, you really want to consider this mirror curve as a ramified covering of some other curve, as we saw in 4 dimensions. So the way that you see it as a covering sort of determines what kind of gauge theory you're talking about. So it influences which BPS states there are, and it influences the whole analysis. So suppose you have a higher genus mirror curve, then first of all, you want to, well, at least from this perspective, we want to identify a gauge theory that it corresponds to by choosing a certain covering. And then, so these wave functions, basically there is a whole basis of wave functions then corresponding to all of the sheets. I'm not sure whether that's.
I have just two very simple questions. One is, when you say abelians, can I picture this as a classical
Well, the Picard, so there is, so this is another part of our paper, but quantum Picard-Fuchs equation is different than the difference equation that I was just referring to. So it's more, so quantum Picard-Fuchs is a relation that you sort of derive from the closed string perspective, but then gives the open periods. So there is I can't say too much about that now, but there is indeed also another perspective which I haven't addressed in this talk, but that's sort of more a closed perspective.
And then my other question was
Is it?
Is the pre-potential
a generating function? I don't know. So right. So so it's 5D generalization is this resolved conifold partition function. So of course that is the generating function of some interesting variables, but I've never seen the 40 limit of that. So I don't know whether that has been studied.
Well, that's